Okay, welcome to this lecture, which is an introduction to UML. So at the end of this lecture, we want you to know the building blocks for how to make any UML diagram, what are the notations, the different kinds of UML diagrams, structural, class, object, components, deployment, and package. So first of all, what in the world is UML? Well, a long, long time ago, in a continent far, far away, America lah, okay? So there was came up with object-oriented programming, and when people first started doing object-oriented programming, they realized that they needed to be able to communicate their design, the design of their programs to other people. So they started drawing little pictures to show them, okay, this is like, here's my object and here's the methods. And so all different people started coming up with different ways to draw these diagrams. And the three most popular ways of drawing these diagrams were done by Grady Booch, which is called the Booch system, and Jim Rumbaugh, which was called the OMT system, and Eva Jakobsen, which was called the OOSE system. And each of these people made their diagrams in order to help people be able to communicate their object-oriented design. Well, what happened was that pretty soon you found people gathering behind them and making them sort of like prophets, saying, oh, you have to use the Booch system. It is better than, what do you mean you're using OMT? No, OOSE is better. And so came the methodology wars. Not quite the Clone Wars, but anyway, people were arguing back and forth about which diagramming system is the best, and wasting a lot of time. And Booch, Rumbaugh, and Jakobsen got together and said, look, this is stupid. Look, we all made our systems in order to help people be able to communicate their object-oriented design. So how about we just get together, the three of us, we get together, we come up with a unified modeling language. And then everybody will just use this unified modeling language to describe their object-oriented design, and we can have peace and no more war. And so that's what happened. Everybody eventually switched to UML, and so now we all use UML and there are no more methodology wars. Yay! Okay, so what in the world is UML? Well, it's important to note here that UML is actually a language for specifying and not a method or procedure. So UML is used to define software systems, the details of the artifacts in the system, and document and how to construct it. It's kind of like, this is the blueprint for building your software, or we're using this to communicate my design. Okay, now programmers implement this design. So UML is used to define a software system and how to construct it. Okay, so the UML may be used in a variety of ways to support software development methodology, like if you're using the rational unified process, for example. But it in itself does not specify what methodology or process you're supposed to use. Okay, so UML, it defines this notation and semantics for these different models. The use case model, the communications model, which is for interaction, the dynamic model, which is for the states, and it's got the states and the logical model, got class and physical model, got components and deployment. So all these things are put in UML. And so why do we need this? Well, people may think that, making software is cheap and easy to produce. Not true at all. Okay, software, especially big software, can be extremely complex. And once you've put a design in place, it may often be difficult and long-winded to try and change it. It's difficult to change. Too much work has to be done if you want to go back and change it later. Okay, so UML helps communications between all parties involved in the software development, whether you're a programmer or you're an investor, whether you're a publicist or an advertiser. And so different people can see and critique it before we actually spend all the time writing the code. Okay, so with UML, you can take a complex system and can break it down into discrete pieces. Then everybody can understand these little pieces more easily. And when you hand over the system to a new team, you've got it all documented, so the handovers become easier. And a complex system can then be understood by the many different developers who are working on different platforms, since UML is not language specific. And the UML model is not a system or platform specific thing. So all these developers can be unified under all one roof. Okay, so let's look at what are these UML components. See, no matter what kind of diagram, the UML notation consists of things, that means entities to be modeled, or whether they're concrete or abstract entities. Then you've got relationships, what are the connection between these different things, and you've got diagrams, which are the graphical depictions of things and their relationships. Okay, what are these things? Well, things, in fact, are the most important building blocks of UML. You've got these different types of things: structural things, which are the static elements of the UML model, whether they're conceptual or physical. And then you've got behavioral things, which are the dynamic parts of the UML model, and they depict different states of the software as it's going through. And you've got groupings, because you've got to group things together and organize the parts and capabilities of UML models. And then you've got annotational things, which are to explain different parts, because sometimes you look at a diagram and there's more going on than is obvious to the view. So these are the different kinds of things. So the first one is structural things. Here you have the class. Class represents sets of objects having similar responsibilities. And here we have interfaces. Interfaces define a set of operations which specify the responsibility of a class. And then here we've got we've got a component, and this is an example of a component, a chain of responsibility. So collaboration. This collaboration defines interaction between elements. And then you've got use cases, which represent a set of actions performed by a system for a specific goal. And sometimes it's a person using the system too. And then you've got components, which describe a physical part of the system. And then you've got nodes. It's a physical element that exists at runtime. Okay, how about the dynamic parts of UML? Okay, dynamic parts of UML model, you've got interactions. Okay, so behavioral things that tell you what's going on between things. So you have these are the two things that are behavioral. One is an interaction, like a behavior that consists of messages being exchanged among things to accomplish a certain task. And then there are states, which define a moment in time that an object goes through in response to events. The events are external factors that control the state change. Okay, and then to group things together, we've got the package, and you can put many things inside one package. So this will collect the different things, many different objects inside, and then you want to have annotational things as well. These are used for remarks, which are descriptions, extended notes, constraints, and comments on UML model elements. And right now, this is the only annotational element available in UML. Now, relationships. These show how elements are associated with each other, and this association describes some kind of functionality of an application. So the kind of relationships we have available are these four: dependency, association, generalization, and realization. And we will be discussing these later using class diagrams as an example. And the same notation can be applied to any other UML diagram. Okay, so here are the types of UML diagrams. We've got structural diagrams, which focus on static aspects of the software system. So these are class, object, component, and deployment. And then we've got behavioral diagrams. This focuses on dynamic aspects of the software system. So you've got use case, interaction, state, and activity. Okay, so UML class diagrams. The class model is at the core of object-oriented development and design. It expresses both the persistent state of the system and the behavior of the system. A class encapsulates state or attributes and offers services to manipulate the state or behavior. Okay, so good object-oriented design limits direct access to class attributes and offers services which manipulate attributes on behalf of the caller. This is so that we don't violate the encapsulation, and you could have you could make mistakes about misunderstandings and whatnot, and then cause all sorts of problems that have side effects elsewhere. So the hiding of data and exposing of services ensures data updates are only done in one place and according to specific rules. For large systems, the maintenance burden of code, which has direct access to data elements in many places, is extremely high. Okay, so here we have the picture, an example picture of how we draw these UML class diagrams. Okay, so here is one. This is the general format. You've got the class name at the top, then you list the attributes down here, and then the methods below. So here's a particular example. You've got this class, okay? The name is class, okay? And it's got age and company and name and other details. And then it got some methods: get age, get set name, update other, and so on. Okay, so so you must be clear that there are these three areas, okay? And you've got the attributes listed like this: attribute name, colon, type, okay? So this is not the way it's done in C, okay? Or not done the way it's done in C++ or Java, okay? And the method names are methods are listed like this. So this is the format in the standard UML, okay? So UML then allows freedom such that when you are drawing a class, you don't have to show all the attributes and operations in every diagram. Because remember, what's the purpose of UML? It is to communicate your design to another human being. So depending on the purpose that you are communicating, if you are trying to do an overview, perhaps you just need to know the name of the class like that. Perhaps in a certain situation, you might need to tell them also some attributes. Some other situation, you need to tell them the methods. And if you're, for example, describing this to a particular coder, they might need to know all the details. Okay, so it depends on the need. You put as much detail as necessary. So the next thing are that there are abstract classes and interfaces. You learned about this back when you were studying C++ and Java. So now here is a way to notate it by using these little brackets, okay, to say abstract or interface. You can do that, okay, because these abstract classes and interface objects are basically classes of objects that cannot be instantiated and are for use by other classes. When you want to make one of these things, you actually have to subclass or implement this, and then you make a concrete object of those things. So like in this case, here's this abstract class of employee, and he's using the italic version. Okay, some people use italic, okay, rather than using the brackets. Okay, so and then these hourly employee, salaried employee, and exempt employee, these are all actual concrete classes of employee. There's no such thing as just a generic employee. It has to be one of these types of employees. Okay, so you can also have a simplified interface object by representing it using a circle like this, okay? And these are also known as component objects from the component diagram. Okay, so these are alternative ways of representing. Okay, in UML, object interconnections, whether they are logical or physical, are modeled as relationships. So the different kinds of relationships in UML class diagrams can be based on two classes, and you can say, okay, here's an association. So what type of associations there are? Associations are saying that, okay, class A communicates with class B somehow, okay? So dependencies means that class A uses class B. So class B has to be defined. If you change the definition of class B, then class A might need to know about it. At least you need to know about the public interfaces, okay? Then aggregations say class A has class B as an attribute. So it actually has a variable storing an instance or maybe a collection of instances of class B. And then composition says class A owns class B as an attribute, okay? So there's it at first glance, aggregation and compositions look quite similar. We'll talk about it in more detail later. Okay, generalizations and inheritance. Class B extends class A or vice versa. Okay, and then realizations is class B realizes class A or vice versa. That means that here in generalization and inheritance, class A has to be a class. Realizations, it could be an abstract class or an interface. Okay, so when we're looking at class dependencies, a dependency is showing that there's some sort of semantic relationship between two or more classes. So in this example, you've got the dependency from course schedule to course, because course is used in both the add and remove methods of course schedule. So therefore, there is a dependency. If you change course, maybe course schedule needs to know about that change. Okay? Especially the public interface of that change. Dependency is shown by this dashed line, okay, with an arrow pointing the direction of the dependency. That means if course changes, maybe course schedule needs to know about this change. Okay, so class aggregation is a stronger version of class dependency, where you have this class appearing as a reference, okay, an attribute of another class. Okay, so inside here, engine, okay, order has an engine, okay, and car has an engine. Car has a wheel, okay, so this is sometimes referred to as a part of relationship. Okay, car has a wheel, car has an engine, or actually car has two wheels. Actually, I would think car has four wheels. Oh well. Okay, so car has some collection of wheels, car has one engine. So this is an aggregation, because this is that's why it's called a part of relationship. Okay, wheel is a part of a car, engine is a part of a car. So both classes remain as strong objects and can exist on their own. So maybe you can have an engine sitting out there on the shelf, it's not inside the car. Okay, aggregation is represented by this diamond shape here, pointing to the part containing the whole. So the car is the whole, the engine is the part. Now, the class composition is a stronger version of class aggregation, where not only is there a part of relationship between class A and class B, there's also a life cycle dependency between them, where one cannot exist without the other, cannot live without the other. You can't just have a leg hanging out there. It has to be always part of a person. You can't just have a hand hanging out there. It has to be always part of a person. Okay, and in this model, I know you can cut off the leg, okay, but that's not the normal way, okay? Ex-murderer, chop off the leg and hand. No. Okay, we're talking about if class A dies, then class B also dies. You kill the person, the leg dies. You kill the person, the hand dies, okay? So in composition, the containing object is responsible for the creation of the life cycle and contained object, whether it's indirectly or directly. Okay, it can be you create something which creates something which creates that. Okay, but the composition is represented by a filled diamond. See, filled diamond here, pointing to the part containing the whole. And a lot of times it's not very clear whether it should be a composition or an aggregation. So sometimes people are a bit sloppy and they're not sure whether it's a black diamond or it's a white diamond. Okay, but in general, the definition is this is what it means. Okay, so and there are associations that just says, okay, there is some sort of relationship, some sort of dependency between these two classes, okay? There's an association between two classes if an instance of one class must know about the other in order to perform its work. So associations are represented with a simple line, just like this line, okay, between the classes. So class dependencies are weak class associations. Class aggregations are strong shared associations, and compositions are strong not shared associations. So this is like, you can say associations are a superclass of dependencies and aggregations and compositions. So there can be multiplicities. Multiplicity basically is an association that can be indicated by adding, okay, numbers to say, okay, how many of this is connected to how many of that. So for example, here you have a student that is connected to only one advisor. Every student only has one advisor, and one advisor can have many students. Okay, a student can learn from many different instructors, and an instructor can teach many students. A student can be a member of many teams, and a team can be a member of a team can have many students, but there's only one president, okay, in a team. So one president the same student can be president of several teams, but the team only has one president. So you can have more than one association between the same two classes. Okay, that's possible also. So you can also have association classes that are some sort of link between the two different classes that they association. You're actually personifying this association. So the relationship between two or more classes involves this other class to represent the link, and so this is how you draw it. And you can also be associated to the same class. Usually it's not to the same object in the class, but another object in the same class. Okay, so a class can have a self-association which associates back to itself. So these self-associations benefit from naming to indicate why this association exists, like sub-team, parent team. See here, employee works for this manager. Okay, so these kind of labels help us, these names help us understand, okay, what is this association, what does it mean? Okay, so, and we don't allow associations between abstract classes and interfaces to avoid looping, because abstract classes and interfaces, you cannot instantiate them. Whereas here, when you have like employee works for employee, right, but it's a different actual employee. It's the same class, but it's a different actual person there that we are dealing with. Okay, so then there's class inheritance and generalization are shown using this triangular shape. A generalization then connects the subclass to the superclass. Okay, so inheritance, you are inheriting. So this child 1, child 2 are inheriting from parent. Okay, and an inheritance usually depicts the relationship between two classes, while generalizations depict how multiple specific classes can be generalized into one generic class. Okay, so child 1, child 2 generalized into this parent class. Both are represented using this solid line with an open triangle as a subclass and generalized n. So actually, a lot of times we don't distinguish between inheritance and generalization. And the only reason you know about it is because of maybe some notation that people put a note there saying, oh, we abstracted this class, this superclass out from these two child classes during a refactory or something like that. Otherwise, actually, it's exactly the same, generalization or inheritance. Okay, so here's another example, or three more examples. You have got whole life policy, variable insurance policy are both permanent policies. Term policies and permanent policies are both life insurance policies. So these are showing you that it is an is-a relationship. Okay, not a part of relationship. This is an is-a. Student is a person. Professor is a person. Variable insurance policy is a permanent policy. A permanent policy is a life insurance policy. Okay, so that's what we mean by generalization or inheritance. Is a, okay, not part of or not has a. Okay, so now we've got class realizations. Example, like realizations are basically specialized relationships that show classes that inherit from abstract classes or interface objects. So here's an interface object, chewable, and we can have an interface eatable, and here's gum, and then there's food, okay, on the assumption that chewing gum is not food, but you can chew it. Okay, you can chew it in my class to stay awake. Yeah, that's one of my staples. I say, if I see people falling asleep in class, I say, Maybe you should get chewing gum. Just don't stick it under the table, okay? Okay, so realizations are displayed in the class diagram as a dashed line, dot, 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 like that, okay? With a closed unified arrowhead that points from the client realizes the behavior to the supplier, which specifies the behavior. So mammal specifies there's a behavior called walk, and then you can have cats and dogs, which actually implement walk in a different way. So object diagrams represent an interface of a class diagram. So they are known as instance diagrams. Object diagrams can be magnified as the snapshot of a running system at a particular moment. So it shows instances instead of classes. See, our class diagrams show classes. Here we show instances, but otherwise it looks very similar to class diagrams. But the difference is that a class diagram represents an abstract model consisting of classes and their relationships, but an object diagram represents an instance of a particular moment which is concrete in nature. So object diagrams are made of the same basic elements, but in a different form. The elements here are concrete form to represent the real-world objects as opposed to an abstract form in a class diagram. So here are some pictures showing it. Like here, you have a particular special order and another particular special order, and they're part of some order which all belong to this customer. Okay, so these are object diagrams. And so this special, whereas the class diagram was here, where the special order is a type of order, and then it belongs to a customer. Okay, so here we have a particular customer, maybe like Ahmad Amiruddin, and he has made an order here, and the special order of maybe popsicles or something, whatever. So these are objects, actual objects, whereas these are classes. Okay, and here's another example where and showing clearly here you've got this instance name. This is the variable, okay, and you've got the class name. This is the class, the department class, and this particular one department, which is called the math stat. Okay. So, and then we've got the component diagrams, which are one of the two kinds of diagrams found in modeling the physical aspects of an object-oriented system. So physical aspects are the elements like executables, libraries, files, documents, and so on, which resides in a node. It does not describe the functionality of the system, but it describes the components used to make these functionalities. So component diagrams are used to visualize the organization and relationships among components in a system. So these diagrams are used to make executable systems, and a single component diagram usually cannot represent the whole system because it's too big. Okay, so what you have is you have a collection of diagrams used to represent the whole. And the component diagrams are used during the implementation phase of an application, but you prepare them well in advance so that you can visualize the implementation details. So here are some component diagram examples. So components are represented as a rectangular classifier with the keyword component, okay, and they can be displayed as a rectangle or a component icon in the right upper hand corner. And the assembly connector bridges the component's required interface with the provided interface of another component to allow components to provide the services to another. See, assembly connector here. And ports may be specified as outputs as they can operate bidirectionally, okay? And an additional notation are borrowed from other UML diagrams like files, packages, whatever you need in your component diagram, okay? So here's another two examples of component diagrams where you've got these things connected together, different components, and these component users. I see these are similar things that we see from the other diagrams. And here's another one. So you've got different components and they're connected together with assembly connectors, and then they deal with other things. And here's another example of a component diagram where you've got these different files, okay? And here's another version where you're talking about the versioning of these files and so on. Okay, so the UML deployment diagram are used to visualize the topology of the physical components of a system where the software components are deployed. So they depict a static view of the runtime configuration of hardware, nodes, and the software components that run on those nodes. They show the hardware for your system, the software that's installed on that hardware, and the middleware used to connect the disparate machines to one another. So it uses the same notation as components with the addition of nodes to indicate where each component resides. So here's an example. This one is residing in the web server. This one is residing in the application server running Solaris, and this one is residing in the database server. It's running Linux, and so on and so on. Okay, so these are more examples where you show, okay, this one is all in the Win 2003 application server, this one's in the main server, business logic, and so on. So different these are different deployment diagrams showing, okay, where are we going to deploy all this stuff that we have designed? Okay, all these components, where are they going to be deployed? And this tells you where it's going to be deployed. This one's deployed in the host machine, this one's deployed in the client PC. And here we have another one showing even going to the internet. Okay, you've got the user here, you've got the connection, and then here is my caching server, and then you've got server 1, server 2, server 3. And here's one where I have a firewall and blocking, make sure that keep this safe, and you have to go through the special what is allowed here, and then you can access some of this data and all that. Okay, so UML packages. You've already seen packages in the UML UC diagram, and a package is basically a collection of logically related UML elements, and they can contain classes and other packages and diagrams. Okay, so here's one that contains other packages. And packages can be used to provide control access between classes in different packages. Packages are depicted as these file folders and can be used on any of the UML diagrams or on its own. And in the example here, you've got here this compiler package has a front end and a back end. Okay, and both are mutually exclusive of each other. Okay, so here's a compiler. You look inside compiler, see front end and back end. Okay. And here's an example of an accounting package and ordering and all this going to the bank and all that kind of stuff. So, in summary, what have we learned today? Okay, you've got classes. Classes tell you this is what the system. We've got class diagrams. Class diagrams tell you this is what the system looks like statically. Okay, these are the parts that you write. Okay, then how they work together, what are the functionalities, and how it's constructed, and what using what. Then you've got the object diagram. This one shows while the program is running, what's happening on. Okay, then you can use this to prototype. Okay, this is what the system will look like when you're doing it, and you can reverse engineer it and use it to model your complex data structures and to actually understand, okay, what's going on from a practical point of view. Then you've got your component diagram, which models all these things: components, database schema, executables, system source code. You've got deployment diagram showing you where to put everything when we are going to deploy the system. And finally, you've got the packages diagram, package notation to simplify any of these diagrams that we've seen so far and group things together. And so that is today's lecture, and we're done. That's all, folks.